All right, so we say a function of two variables is continuous at a point AB if the limit as xy goes to AB, the limit of our function f is exactly f of AB. This is exactly the same definition that we wrote down for continuity back in Calc 1. This limit is actually telling you three things. One is that the limit exists. Two, the function is defined at AB. And three, these things are actually equal. So same definition we saw, should be no surprises here. In Calc 1, we would talk about being continuous on an interval, and we talked about maybe from the left, from the right, all those kinds of things. We're going to just focus on continuity on a set. And so what does that mean? Well, you have some subset of the xy plane. Maybe this is the subset D. So you're continuous on D if you're continuous at each point in D. And we could get a little more complicated and talk about more details, but for our purposes, this will do just fine. So in Calc 1, when we introduced continuity, we said that you can think about continuity as basically just saying when you graph the function, you don't pick your pencil up. There's no holes in the graph. There's no jumps. And the same intuitive idea is true for continuity of functions of two variables. There are no holes or tears in the surface. The difference is instead of a curve in 2 space, we have a surface in 3 space. All right, so second remark is that sums, differences, products, quotients, compositions of continuous functions, they all remain continuous as long as you're careful with domain restrictions. I'm not going to say any more than that. Here's the takeaway that I want you to have, okay? Everything works more or less the way that you think it should as long as you're careful with domain. So when you look at a function, you should be able to tell quickly whether it's continuous at your point or not. All right, last remark is that polynomials in two variables, it's important that we recognize these are always continuous. They're continuous at every point on R2. And then rational functions in two variables are continuous on their domains. So if the point is in the domain of the rational function, then the function is continuous there. So let me show you how this is sort of useful. Here's a limit that we might be asked to evaluate. And we just look at the function and we recognize, oh look, that's a polynomial in two variables. Polynomials are continuous everywhere. They're certainly continuous at the point 1, 1. And so I can just plug in. When I want to compute this limit, I can just say, well, this is going to be what? 1 minus 1 plus 3 plus 2. This is just 5. Done. That's it. Whereas we can look at this function and we can say, okay, arctangent is continuous everywhere. So I don't need to worry about the output of this, just the input. What goes into the inside here? Well, this is a rational function. It's continuous everywhere that it's defined. The only place it's not defined is along this line y equals x. And so we can say that this function is continuous on R2 except along the line y equals x. So if you wanted to graph the domain, you could say, look, the domain of this function is actually everything except that line. It's everything but the line y equals x. Here, let's do this, and then we can just fill it in. So that's the idea with domain. I thought you might like to see how what this function actually looks like. So I'm going to switch over to my GeoGebra app and see if I can pull it up for you. So let's see here. Here it is, and then whoop, it's not wanting to open. There it is. We'll lay it right here on my phone. It's a great place. Oh, it doesn't like it. There it is. Technical difficulties. Okay, so let's zoom in a little bit. My fingers must be sticky. I can't control the screen at all. Let me see here. Whoa, sorry. I'm wobbling the iPad, and so it's jerking the screen around. Okay. So there's the line y equals x. You can kind of see it in 2 space. What GeoGebra has done is to go ahead and fill in the jump for you, so it looks like it's this solid surface. That's actually incorrect. There is no surface that's vertical there. And so Mathematica often will do the same thing. not a huge deal, but just be aware of that. It's trying its best to graph this, and that's what it came up with. So anyway, that's a rough sense of what it looks like. And we'll end this video and this section here.